Hello, in today's video we are going to focus on vectors, which is a very important topic both at the advanced level pure mathematics as well as further pure mathematics. This time we'll be looking at a short method for getting the Cartesian equation of a plane when three non-collinear points on the plane have been given. I have decided to treat it as a equation so that you clearly see how it comes about, but in particular the first part, which is involving the proof of the formula, I just focus and make sure that you get how the formula comes about. It is in the second part of the equation where you have to pay attention and see how the short method works for the case of finding the vector equation of a plane that contains three non-collinear points. I've decided to present it in the form of equation, and it says prove that the Cartesian equation of the plane containing the non-collinear points A with coordinates x1, y1, z1, B with coordinates x2, y2, z2, and C with coordinates x3, y3, z3 is given by the determinant of the matrix x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, and z3 minus z1 equals 0. Hence, find the vector equation of the plane containing the non-collinear points A with coordinates 1, 2, 3, B with coordinates 3, 0, 1, and C with coordinates -2, 1, -1. Okay, we begin with the first part, which involves the proof. If the equation is given in the exam, like the last part of the equation, finding the vector or Cartesian equation of the plane when the 3 points have been given, you just proceed to state the formula and then do your substitution. You do not need to do the proof while you are applying the formula to solve, so take note. The formula has been proven in this video just for you to be convinced how it works. So to begin the proof, here is a diagram of the plane. Note that a plane is any flat surface, like a disc, for example, is a plane. So this is a rectangular plane, and on the plane we have the 3 points that have been mentioned in the equation: point A, point B, and point C. And to further proceed with the proof, I have indicated a general point P with coordinates x, y, z, since the Cartesian equation would have to involve that general point. So the first thing you would have to do is to fix one of the points and then get displacement vectors of that point with the other points. So 3 vectors that are embedded in this plane involve the displacement vectors AB, AC, and AP. And we can further proceed to obtain those vectors. So I begin with AP, which is actually OP minus OA, and that should then give x minus the x coordinate of A, which is x1, y minus the y coordinate of A, which is y1, and then z minus the z coordinate of A, which is z1. In a similar manner, we have vector AB, which is supposed to be OB minus OA, and it has components x2 minus x1, y2 minus y1, and z2 minus z1. In the same way, we also have vector AC, which is equal to OC minus OA, and corresponds to the vector components x3 minus x1, y3 minus y1, and the z3 minus z1. Now, a vector normal to the plane is n and is given by AB cross AC. Remember, the cross product of any two vectors is always perpendicular to the two vectors, and since the two vectors are embedded in the plane, it means that their cross product is also a normal vector to the plane. So AP is perpendicular to AB cross AC. So we note that AP dot n should be equal to 0 since they are perpendicular vectors. And so we can now write that AP dot AB cross AC, since n is AB cross AC, that should be equal to 0. Now the first thing we're going to do is to find AB cross AC, which should be equal to determinant of the matrix I, J, K, and then we have AB as x2 minus x1, y2 minus y1 and z2 minus z1. We have AC as x3 minus x1, y3 minus y1 and z3 minus z1. And we then have that the expansion of that determinant would give I into y2 minus y1 into z3 minus z1 minus y3 minus y1 into z2 minus z1 minus j into the minor of j, which is x2 minus x1 into z3 minus z1 minus x3 minus x1 into z2 minus z1 plus k into the minor of k, which is x2 minus x1 into y3 minus y1 minus x3 minus x1 into y2 minus y1. Having obtained the cross product of AB and AC, we now proceed to find the scalar triple product, which is now AP dot AB cross AC. So from there, we simply multiply the I component of AP by the I component of the cross product, the J component of AP by the J component of the cross product, and the K component of AP by the K component of the cross product. And if you observe carefully, you would see that AP dot AB cross AC is the expanded form of this determinant. Since AP and AB cross AC are supposed to be perpendicular vectors, the dot product being 0, it means that this determinant should then be equal to 0, and that gives us the proof that we're required to do. So when you have a question which asks you to find the Cartesian equation of a plane containing 3 non-collinear points, you simply make use of this relationship in order to save time in the exam. The method is very short and straightforward. Now let us proceed to apply it in a question as was given. We were now asked to hence find the vector equation of the plane containing the non-collinear points A, B, and C. To apply the formula in this question to find the Cartesian equation of the plane containing A 1, 2, 3, B 3, 0, 1, and C -2, 1, -1. So if in the exam you have been given a question under vectors which requires you to find the Cartesian or vector equation of a plane containing 3 non-collinear points as presented here, you just proceed to state your formula from x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1 equals 0. And proceed now, go to your points and indicate x1, y1, z1, x2, y2, z2, x3, y2, y3, sorry, and z3. And you come and replace them in the formula and then proceed with your solution. So we just have the general x minus x1, and x1 is 1. We have y minus y1, and y1 is 2. Z minus z1, and z1 is 3. And then we have x2 minus x1, so x2 is 3 minus x1, which is 1. y2 minus y1, y2 is 0, and y1 is 2. Then we have z2 minus z1, z2 is 1, and z1 is 3. We have x3 minus x1, x3 is -2, and x1 is 1. We have y3 minus y1, so y3 is 1 and y1 is 2. and we have z3 minus z1. Z3 is negative 1 and z1 is 3. That determinant should be equal to 0. Then we proceed to simplify x minus 1, y minus 2, z minus 3, 2, negative 2, negative 2, negative 3, negative 1, negative 4 equals 0. X minus 1 into the minor of x minus 1, so we have 8 minus 2 minus y minus 2 into the minor of y minus 2, which is negative 8 minus 6, plus z minus 3 into the minor of z minus 3, which is negative 2 minus 6. That should be equal to 0. We have 6 into x minus 1 plus 14 into y minus 2 minus 8 into z minus 3 equals 0. 6x minus 6 plus 14y minus 28 minus 8z plus 24 equals 0, so that we have 6x plus 14y minus 8z equals negative 6 minus 28 is negative 34 plus 24, negative 10. Sending it to the right hand side will give 10, and we can further simplify to have 3x plus 7y minus 4z equals 5 as the Cartesian equation of the plane, but we were asked to find the vector form of the equation. So the vector form would simply be x y z dot 3 7 negative 4 equals 5, and xyz is the position vector of a general point, usually denoted r, on the plane. So r dot 3i plus 7j minus 4k equals 5 would be the vector equation of the plane that has been asked in the question. So, but most of the time they would only ask you the Cartesian equation, which is here. We can verify by substituting any of the 3 points that we have had in the Cartesian equation to see if it satisfies it. Let us consider the first point, which was given as 1, 2, 3, lying on the plane. If we substitute it, we would have 3 into the x coordinate, which is 1, plus 7 into the y coordinate, which is 2, minus 4 into the z coordinate, which is 3, and it should give 5 if the point lies on the plane. So we have 3 plus 14 minus 12, which is equal to 5, and 17 minus 12 gives 5. 5 equals 5, and that shows that the point lies on the plane. You can do the same with the other 2 points which have been given, and you would see that they always satisfy the equation of the plane, showing that the formula is valid. So again, before we end, the first part involving the proof has been done just for you to see how the formula comes about. You would not need to do the proof when the question has been asked, except the proof itself has been given as part of the question. You would mostly just be given 3 points that lie on a plane, and so long as they are non-collinear, they will ask you the Cartesian or the vector form of the equation of the plane. Then you just proceed by stating the formula and applying it without showing the proof. So take note. Thanks for watching, and if you are new to the channel, please consider subscribing and activating the notification bell so that anytime we post a new video, you will get it and then watch. Also support us by liking and commenting on the videos, and especially sharing to your friends so that they get to know more about the channel, which has a lot of important resources concerning your examinations.